Hi everyone, in this video I'm going to go over naming acids, so let's get right into it. The first thing you have to know in order to name an acid is whether it falls into a category of binary acid or oxyacid. There's plenty of ways we categorize acids, strong versus weak, mono, di, triprotic, but in this case when it comes to naming we have to know is it binary or is it oxy? So let's go into those categories. A binary acid, it's hydrogen bonded to one other element. So binary means two. So it's H and then one other element. So these are going to be your things like hydrogen bonded to chlorine, HCl, 1, 2, or HF, or HI. Okay? Now keep in mind that second element might have a charge that's different from -1. Notice chlorine, fluorine, iodine all form -1 anions. So when they bond with hydrogen, which is 1+, they're going to form 1-to-1 ratios. But let's say hydrogen bonded with sulfide, which is sulfur turned into an ion. Well, hydrogen is plus, sulfur is 2-, so what's the formula going to be? H2S. Now this is still considered binary because it's two elements, even though there's technically 3 atoms here. So things like H2S or H3P, these are all going to be binary because it's one element, hydrogen, plus one other element. The other category is oxyacids. This is going to be hydrogen bonded to a polyatomic ion that contains oxygen. So your polyatomic ions, you should have some kind of list for these. Most of them contain oxygen. If you look at a list of polyatomic ions like I have here, the overwhelming majority of these contain oxygen. There's a couple that don't. For example, ammonium right at the top doesn't have oxygen in it. Well, ammonium's not going to bond with hydrogen anyway because ammonium is a positive cation and hydrogen always bonds as H+ in the case of acids. So you're never going to get like an ammoniic acid. There's no such thing. So don't worry about ammonium. It's never going to form an acid. But most of these other ones contain oxygen. There are a couple that don't. At the end of this video, I'll try to remember to address those. But oxyacids are the polyatomics, the vast majority that contain oxygen. So for example, one of the most common polyatomic ions is nitrate, which is NO3 with a minus charge. When hydrogen bonds with this, it's going to be H+. So what's the formula going to be? Well, it's a 1-to-1 ratio. It's just going to be HNO3. So that's going to be one of your oxyacids. Or you can have hydrogen bonding with carbonate. Carbonate is CO3 with a 2- charge. Well, in this case, we have H+ bonding with CO3 2-. How many of each of these do we need? Crisscross rule, H2CO3. So these are examples of oxyacids. Okay? Now let's go into how we actually name these. Starting with binary acids. For this, you're going to say the word hydro first. Not the full word, it's the prefix. So it's going to be hydro. Then it's going to be the sort of root word of the anion. So, let's say this. 1 hydro, 2 root word of the anion. For example, if the anion is chlorine, so we have HCl, okay? 1H, 1Cl, this is binary. That's chlorine, the root word of that is chlor. Or HF, fluor. Or HBr, brome, BROM. Okay? Hydro plus the root word of the anion, and then at the end you add ic. They're all ic, and then 4 is acid. Or really, we should say step 3 is ic acid, like this. Okay, so it's a simple 3-step process: hydro, root, ic acid. Now, I'm sure many of you coming into chemistry already knew the name of HCl. Hydrochloric acid. Use that as like your template. So again, it's binary, so we're going to say hydro, we're going to say the root word of chlorine, which is chlor, and then we're going to say ic acid. So let's make a list of some of these. Well, HCl is hydrochloric acid. Okay. Now, Wilden chemistry people, we all know that acids have to be aqueous. If you're watching this for VHS, we'll get to that later. Aqueous meaning it's dissolved in water. Technically, if you just have HCl by itself, that's not an acid. That's hydrogen chloride, which is a poisonous gas. Once you dissolve it in water, then it becomes hydrochloric acid. Okay? So HCl hydrochloric acid. Another binary acid would be, let's just kind of run down the list of halogens, HF, aqueous. That's going to be hydrofluoric acid. Now, it's not hydrofluoric. There's no such thing as fluorine. It's fluorine, F-L-U-O. So it's hydrofluoric acid. Okay? HI, aqueous. I'm kind of skipping around. Whoops. Hydroiodic acid. HBr, aqueous, is hydrobromic acid. Now there are more halogens. There's technically astatine, and the new one is tennessine. But these aren't really going to form acids because they're radioactive. They don't really exist. In fact, astatine is going to be probably more metallic than non-metallic at this point. But really, the top four halogens are the only ones that are going to really react in any serious way. So these are four of the binary acids, but we're not done. There are a couple others that they can form. So if the hydrogen bonds with sulfur, well, it's going to be H2S, which I explained on the last slide. How do we know it's H2S? Because sulfur forms a 2- ion, and hydrogen is a 1+ ion. So you're going to need to crisscross those numbers and say H2S. The same rule applies here. We're going to say hydro. Now you might think sulfur, the root is sulf, so you might think hydrosulfic acid. Totally reasonable. That's just not what it is. So you're just going to have to sort of memorize. We don't say hydrosulfic acid, we say hydrosulfuric acid. So in this case, the root is the entire word. We can also say, let's see, hydrogen bonding with phosphorus. That's going to be H3P. Why H3? Because P forms a 3- ion, so it's going to need 3 hydrogens to cancel it out. So you might think this would be hydrophosphic acid. Again, the root of this is phosphor. So it's going to be hydrophosphor. Let me spell this right. Hydrophosphoric acid. Okay. Now there might be a couple more that you can encounter. If you have H3N, that's going to be hydronitric acid. This is not very common. You might not really see this one. If you have H bonded to selenium, it would be hydroselenic acid. I think hydroselenic. Again, there are some that are so rare you're really not going to encounter them. I say the real common binary acids you're going to come across are going to be the 4 halogens plus these 2. So be familiar with these. But you should be able to, in theory, name what the acids would be if it were another nonmetal. Let's cover oxyacids. Now this one, there's a lot more examples we can do because there's hundreds of polyatomic ions. And really, common polyatomic ions, there's about 20 of them that contain oxygen. So the rule for naming oxyacids, it's not hydro or anything like that. The rule is adic-itis. Adic-itis. Sounds like random sounds, right? Well, it actually makes sense. You'll notice that all of your polyatomic ions here that contain oxygen either end in ate or ite. Your ates are going to become your ic acids. Your ites are going to become your us acids. And the key here is this: no hydro. No hydro. For oxyacids, you do not say hydro. So let's go through some examples. Well, one of the most common polyatomic ions is nitrate. Nitrate is NO3 with a minus charge. Well, when hydrogen bonds with this, what's it going to form? HNO3, aqueous. Okay? So again, this is nitrate, HNO3. What's that going to be called? We're not going to say hydro. We just say the name of the polyatomic ion, but we change the ate to ic or the ite to us, and then we add the word acid. So nitrate just becomes nitric acid. Ate, ic. Ates become ics. Nitric acid. Well, let's do the brother of nitrate. Let's do nitrite, which is NO2 with a minus charge. Well, when this bonds with hydrogen, you're going to get HNO2. Again, this is nitrite. And that's going to form, well, ite, us. Ite, us. So it's going to form nitrous acid. Okay, so that's nitrous acid, nitric acid. Adic, itis. Okay, a couple little sayings we use to memorize these. I ate too much, I feel icky, or I feel sick. For ite, us, there were a couple good ones. Oh, a snake bite is dangerous. There's a couple others you can come up with. Let's do a couple more examples of oxyacids. For example, let's say hydrogen bonds with acetate. Acetate is C2H3O2. It can also be written as C2H3OO, just so you know. So when this bonds with that, well, this has a minus charge, and this is plus, so it ends up just being HC2H3O2. Aqueous, of course. Okay, so that's the compound, HC2H3O2. You might say, well, why don't we just put this H with these and call it C2H4O2? You don't want to do that, because the H in front shows that it's still kind of, like, this is still technically a compound that can split up in water, especially since this is a weak acid. But you want to show the H in front, again, because the presence of the H in front separate is what makes it an acid. You don't just combine the H with the rest. Anyway, let's get to naming this. I mentioned before that this is acetate. Well, ate-ic, right? So acetate is going to turn to acetic acid. Acetic acid, which is vinegar. Vinegar is about 5% strength acetic acid. Let's do another one. CO3 minus. This is carbonate. This is carbonate. Well, what's it going to form when it becomes an acid? If hydrogen bonds to this, we're going to get H2CO3. Why two H's? Because this is 2 minus, so you need 2 H pluses to balance it out. And what are we going to call this? Well, carbonate is going to become carbonic acid. Okay, so adic, itis. Here, why don't you practice a few of these? There's a common group of polyatomic ions that go like this. ClO minus is hypochlorite. Hypochlorite. ClO2 minus is chlorite. Chlorite. Come on. ClO3 minus is chlorate. And ClO4 minus is perchlorate. So these are 4 common polyatomic ions. What you should do is pretend these are going to form acids, write what the compounds are going to be, the formulas, and then name them. Why don't you pause the video and try that now? Okay. So ClO4. Well, let's write the acids first. Notice minus, 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 minus. This is not 2 minus. It means there's 2 O's, but there's still a charge of minus. 3 O's, but still a charge of minus. So all of these are going to get 1 hydrogen. So let's just fix that right now. And technically, all 4 of these are going to be aqueous as well. So let's change hypochlorite, chlorite, chlorate, and perchlorate into the acid forms. Well, it's as simple as saying adic, itis. Hypochlorite, ite, ic. Itus. Hypochlorous acid. Itus. Chlorite, chlorous acid. Chlorate. Atic. Chloric acid. Perchlorate. Atic. Perchloric acid. So those are the rules. For your oxyacids, which are the polyatomic ions that contain oxygen, which is most of your polyatomic ions, it's atic-itis, no hydro. For binary, which is when it's just two elements like this, hydrogen and one other element, the rule is hydro, then the root, and then ic acid. And use hydrochloric acid, which you all know, as kind of your template. Now before I wrap up this video, there are some polyatomic ions that don't contain oxygen. For example, CN is cyanide, CN with a charge of minus. So if we have the acid form of that, which is going to be HCN aqueous, what are we going to call that? Are we going to call it binary? Or are we going to call it oxyacid? Technically, it's neither. Well, technically, I believe they consider this to be binary. But it's kind of halfway between, in my opinion. In this case, we go with the binary naming rule. We don't go with oxy. You're not going to call this, I mean, you can't go by the oxy acid because it's cyanide. Ide doesn't fit in there. So we're going to go with hydrocyanic acid. So there's a couple kind of examples that are caught in the middle, but most of them are going to fit the rules we already mentioned. Okay, so that's it on naming.